it's time to welcome new Sage developers. Among the audience, who of you identify as new Sage developers? Would you mind raising hands? Not seeing any. Okay. Oh, great. Would you like to introduce yourself to the community and maybe draw people's attention to your latest development on Track Sage? Maybe can attract attention so the tickets gets reviewed quickly. Let's see. David, hello.
Hello. Hi.
Hello.
Yeah, I'm David. Let's start with. Hi, I'm David. I will be speaking in an hour or so about my Google Summer of Code project, and I've been contributing SageMath since last summer. I participated in 2017 in Sage Days, but at the time I wasn't too much. I didn't have a lot of experience with Linux and programming, so I wasn't very confident with the Sage development. But the Google Summer of Code helped me a lot learning about development, and I have some tickets right now, and I work with modular forms, and yeah, that's about it. I don't have any question.
Okay, I guess we will hear about your presentation just in a few minutes. If you have questions about Sage developers or experts in the field, feel free to ask. I saw somebody else raised hand. Nicole Lee, would you mind presenting yourself?
Hi everyone, I'm Nicole, and I'm the student of the Google Summer of Code this year, and I'm the new developer. I think I'm the new developer of the Sage, and I've been making some document changes in the Sage and working on the real set right now. Yes, and I've been having some problem with Sage track and report something. And I'm really excited about this Google Summer of Code this year.
Great, welcome. And who else? Allison?
Hi, is my audio okay?
Yeah, great.
So I'm Allie. I'm a fourth year grad student at UK, the University of Kentucky. I'm new to Sage development. I just started a couple of months ago, and I actually have some tickets on track. If someone here wants to review them, I'd really appreciate it. 33656 and 33752. Thank you.
Okay, thank you. Do you have any advice for new developers in Sage, like how to deal with track and what's the best workflow, stuff like that?
I would say start with something small.
Good advice.
Don't start with a whole new large package of something, but find a small bug. Even correcting the spelling in a doc string will teach you how to make patches and commits and upload them without having to worry too much about complicated details.
I strongly agree with that advice. With most projects I've contributed to, it's like I start with a spelling error and make a fix, because there's always little things like that. And then you get a sense of the workflow without the difficulties, but everybody appreciates it.
Or try to implement something really small, although sometimes you might think something would be trivial and it turns out to be harder than you thought. I think I once decided that elements of Q bar didn't have an is square method, which of course should always return true. But by the time I'd spent half a day on trying to apply this to QQ bar and the real subfield, it got so complicated. I think I gave up. I don't know if that has even ever been done. But start with something trivial that should be there and isn't.
What would be the best ways to get involved and interact with people? Like if me as a new developer want help, ask a question, where can I ask a question? And yeah.
Well, of course, there is the Sage Dev list. So I think each new developer should subscribe to that list. And also each new developer should, it's quite obvious, but it should give a look to the developer's guide, which is pretty up to date, I think now. So there are many advices, many examples in that guide. So it's worth to spend some time to read it, I guess. It's
yeah, the new developer's guide is very well explained. I mean, it is very long, but don't be terrified by the length. It is very well organized. All the sections have very explicit titles and section titles. If you search for a keyword, I'm sure most of the questions will be answered by the developer's guide. Otherwise, there is the Sage Developer Group. And what's the difference between Sage Developer Google Group and Sage Support Group? And there is the forum Zulip, also Ask Sage. Are there any differences, or which is the forum to use for which kind of questions?
Well, I would say that Ask Sage is for more for user questions about how should I do this and things like this. As far as I understand it, Sage Support is more for installation issues, more technical issues, not mathematical questions, more practical question installing and using Sage. And developer forum is for really developing and things like this, and reporting bugs as well.
If I somehow find a bug that I think is a bug because the return of the Sage code it does not meet my expectation, should I ask on Sage Developer Group, or should I, for example, just open a ticket?
I usually ask first before opening a ticket. You should certainly you should always look to see if there's already a ticket before opening a ticket, but it can be quite hard to find.
That's a great point.
There are some Sage Google groups which are a bit more specialized than Sage Devel. They're not used that much, I don't think. I mean, I started a Sage number theory, which is called Sage-NT. I started that years ago, and occasionally things come on there. There are people who subscribe to that but don't subscribe to Sage Devel, or at least they don't read it all the time. There must be some others of those. I hope there's a list of them somewhere. I'm not sure where that would be.
I think on the Sage website.
Yeah, should be.
Okay, thanks for the great advices. Yes, William just put the link, develop group. I haven't seen this before. That's new.
So if you go through the little menus at the top of the website, there's one labeled development and has mailing lists. And there's another one labeled help and it has mailing lists. And one of them is the mailing lists. They're supposed to be for helping users out. And the other is the mailing list. They're supposed to be around development. Because probably Harold just decided that's how to categorize them into 2 different categories at some point, is my guess.
I see. Thank you. Do we have any other questions? Okay. Then we'll just take a little break until, well, for noon EST. We'll have 3 students presentations, and you may stay in the Zoom meeting for spontaneous discussion. Okay, welcome back. This is the session for Google Summer of Code presentations. We have 3 speakers from last year's program. Our first speaker today will be Linden. I'm not sure I read your name correct. Linden Disney-Hogg from University of Edinburgh.
Perfectly correct. Thanks very much for the introduction, and yeah, thanks to the organisers for having me here today. It's a great pleasure. We're going to sort of, obviously we've only got half an hour, so we're going to get absolutely flying today if we can. We're going to sort of have a basic breakdown today. We're going to talk a little bit about the problem and sort of motivate it. I'm going to talk a little bit about the work that I actually did on the Summer of Code last year, and then we'll talk a little bit about what that code can be used for, and then where we might want to go in the future with some of that. So to get started, you know, I'm a mathematical physicist. That's sort of my background. So I'm going to give you a mathematical physicist introduction to this problem. So sometimes in dynamical systems, we have certain integral dynamical systems which have great properties, and some of those have what's called a lattice pair, which is a pair of these matrices such that the dynamics of the system is encoded in just this commutation relation. And it's quite easy to show that L has this property that it's isospectral, so that the eigenvalues don't change throughout time. This dot over the L is meant to sort of indicate a time derivative there. So now if L depends on some complex parameter, we can take the characteristic polynomial of L, and this is going to define as a Riemann surface, which if you're not familiar, so I'm not certain of the background of people here, whether you're sort of more maths or more computation, but for us today, a Riemann surface that can be a one-dimensional complex manifold. It's going to be connected, and it's going to want to be compact. And we're going to call that, because of sort of the history, we're going to call this particular characteristic polynomial the spectral curve. So here's an example that's sort of relevant to the work that I do. It's in NARMS equations, and they have this particular lattice pair. And it's sort of the function theory of this Riemann surface can often be used to actually reconstruct solutions to the dynamical system. So that might be why you want to actually start looking at Riemann surfaces associated to dynamical systems and do function theory on Riemann surfaces, which is really where we headed here from. So just to give a brief overview of Riemann surfaces, as I said, because I'm not sure what everyone's background will be, it was first implemented 5 years ago in Sage by Broin, Sichling, and Zotin. I have to put my hands up here and say I'm biased. So Broin was my mentor for the Summer of Code. So anything I say about this paper and how great it is immediately biased, and you can't take my word for it. But so this implementation, we're just going to need 2 things for a Riemann surface. So we're going to need a base field, which can be a subfield of the complex numbers, which is going to take a polynomial in 2 variables. If you care about things about projectiveness, this is an affine chart of projective curve. And then because of our computations, we're going to need some sort of number of binary digits of precision. This is just because all the things we can do won't actually work exactly. So we're going to want to do some actual multi-precision calculations. When we've taken K as our base field here, we've actually sort of often going to need to work with it being the rational numbers, and we'll sort of discuss with the reasons for this why. Even if it's algebraic, that's still a little bit of a restriction, but you know, Riemann surfaces with algebraic base field are dense in all Riemann surfaces. That's sort of helpful. That's a good theorem there. And then, you know, Riemann surfaces are going to come with sort of one integer. It's going to give us some topological information. It's going to tell us about these 2 cohomology, or one cohomology and one homology class, which we're going to think of this H lower 1, which is homology. We're going to think of these as closed cycles on the curve, and H upper 1, this is this cohomology. We're going to think of these as holomorphic differentials. If you know what these are, great. If you don't know what they are, don't worry too much about them, but they're going to sort of form part of the construction that we're doing here. in the sense that all we're going to need is the fact that we can integrate differentials over paths. You know, this is sort of standard when we think about integrals over a segment. We can extend these to paths on manifolds and these differentials. And I'm going to sort of think of that as a pairing between these two spaces. So I mentioned that I called this H lower one homology. If you know what that is, again, great. But otherwise, we're going to want a homology basis. So we're going to think of this Riemann surface, which I'm now going to call X, as a branched cover of the complex numbers. We'll see a little picture of that in a minute if you're not familiar, to sort of get your head down. And there's going to be a certain set where this branching is going to come together, or we're going to have singularities. So usually we have a cover with a certain number of sheets. These sheets might sort of coalesce at some point, and we're going to call that the branch locus. And we can then create a set of cycles by sort of putting points at this branch locus and then taking a Voronoi diagram around them. This is sort of a really helpful way of doing this, because these paths, which are then going to start to contribute to a homology basis, is going to avoid these bad points, this branch locus. And then actually, once you've done this, you can lift using certified homotopy continuation to the Riemann surface. Remember, I said this was a cover, so I get some sort of paths on a base and I can lift these up. And then we can just get a basis with graph algorithms, and we're all sort of hopefully happy with the graph algorithms are very good and have done well in Sage. And then I'm going to sort of want to tell you that I'm going to put some sort of particular structure on this H1 to make it a symplectic Z module. And this just allows us to canonicalize a basis, again, using sort of tools that exist within Sage. As sort of a side remark, the algorithm that works for doing this in Z modules does work for any PID, but it's sort of noted in the documentation that that's not been implemented yet. So if that sounds good to you, you can go away and implement that today. So this is just going to be a quick picture to sort of cover what I've just said there. You can see these little red dots are going to be the branch locus, as we've said, of this particular Riemann surface. You can hopefully see these little blue dots, which are then going to be these this Voronoi skeleton downstairs, and then one will need to lift it up. So here's a little picture, which I was going to make my own picture, then I decided that the cover of Sheferovich's book was just too nice, and so I thought I'd steal that quite blatantly. So hopefully you can see here down at the bottom, there's some sort of plane, and we're covering it above. There's some point where these all come together. We also mentioned cohomology, which was this other sort of H with an upper one. And there's going to be two ways that we're going to get this cohomology basis on our Riemann surface. We can either use it doing sort of monomials, using it sort of a result in a Newton polygon, or we have to do computations with the adjoint ideal. This first method is great because it's fast, but you sort of require some results from Baker's theorem for it to apply to a Riemann surface. And that's not true for all Riemann surfaces. It's true for a lot of surfaces that we care about, like hyperelliptic curves, but it's not always going to be the case. Alternatively, we can do these calculations using what is here. I've said the adjoint ideal for this Sage interfaces with singular, but these calculations in singular require this base field, this field K, to be the rational numbers. This is sort of one of the restrictions that I mentioned earlier. Macaulay or Maple can actually do these calculations themselves and can go up to algebraic base field. So something that, you know, in sort of the mission statement of Sage, we might want to push that forward at some point. Now, with these two objects, this homology and this cohomology, I said we've got a pairing. I'm going to create what's called the period matrix, which is just doing these integrals sort of over my basis. And then I can construct what's called the Arbol Jacobi Map. And this can be one of the big things, one of the big ticket items about this work that I did for the summer of code. It's going to be implementing this Arbol Jacobi Map. This map is just an integral along a path of all this basis of differentials, so it's vector valued. And you might want to tell me, oh, look, it depends on the choice of path, and that's true. So we often leave quotient out by sort of the vectors that are integrating over these closed paths. And hopefully you can see that those are exactly the vectors that are the columns of this period matrix. So actually this goes into a space that's called the Jacobian. Sage does have some implementation of the Jacobian, but that's not sort of unified yet. Again, we'll talk a little bit about that later. And you can extend this linearly to divisors, which for us will just be the free Z module on points in my Riemann surface. So when I've written this Arbol Jacobi map from P0 to P, I've picked a base point P, which is some point on my curve. I'm going to another point P on my curve. I'm choosing a path and I'm integrating along it. And how we choose that path is something that we'll talk about later. We're actually going to do calculations in Sage. So to give you a brief example, because obviously we've sort of flown through that bit on Riemann surfaces, hopefully you might know a little bit about elliptic curves. You might know that they have this Weierstrass P function. And the Arbol Jacobi map with base point to the infinity on this curve, if you sort of think of the standard Weierstrass form of elliptic curve, that is just the inverse map of this Weierstrass P. So that should sort of to you hint that the Arbol Jacobi map is going to be useful, at least to me, sort of as a mathematical physicist, because it's inverting sort of a tricky function. And that sort of inverting process is sort of what we want to do when we're thinking about the spectral curve motivation. Now, there is another sort of part to this work that I did on the Summer of Code, which we'll just talk about again quickly, which is rigorous integration. So when we're doing these integrals that we're doing for the period matrix, because we said that we've got this Voronoi diagram, these paths are going to reduce to piecewise linear, so they're going to reduce to these integrals of some sort of algebraic function g. And we want to approximate those. This is just numerical approximation of integrals. We all know this. We take some weights, we take some nodes, we sum them up, and we want to get particular error tolerance. And the particular scheme for this integration that we're going to use, or we do use in the code, it's going to be Gauss-Legendre. So these xk are roots of Legendre polynomials. These weights have this sort of funny form. And all that's really important about that is you need to know that every time you want to calculate these x for a given n, you have to redo that calculation. There's no way to sort of start with n and then build up to the node for n plus 1. You have to do that again. And it's about an order n squared algorithm to calculate these weights and nodes. So that was sort of lightning. We've gone and covered a lot of stuff. If anyone has any questions at this point, please do let me know. Otherwise, we'll crack straight on. Perfect. So Summer of Code, that's what I did last summer between June and July. And it was sort of implementing some of these ideas. So we're going to have a better way to do Gauss-Legendre integration, and then we're going to actually implement this Arbol Jacobi map in Sage. So this is this rigorous integration. I mentioned that we have to do this n calculation if we want to do Gauss-Legendre integration. And the previous method implemented by Nils used an error bound from this reference. And effectively, you just have to keep doubling n each time. And you have sort of this heuristic, which says, how is your error progressing? And you can hopefully see that that gets quite bad quite quickly. If, you know, we're doubling n in this algorithm, this order n squared. So we want to do something better. And what we're going to do is we're going to use this theorem, which says that if we have this g, this integrand of this Gauss-Legendre, it's holomorphic on some ellipse, and that we've got a bound for its modulus on this ellipse, then we can give the error of this integrand, so that's the error between the integral and this numerical approximation, has this closed form. And you can get tighter bounds in this closed form, but what's important to see here is you can actually invert that error bound to get a particular n. You know, move that e to the 2nr to the other side, divide down, and you can get a particular n to achieve any given error that you want. To utilize this error bound, you do have to have a method for calculating n, and that's what we're going to discuss in a little bit. And that's the subject of a preprint that Nils Broin and I, student Effie Gower, have got in the process. And at this point, I should sort of stop and say that we're not the first people to use this error bound in Gauss-Legendre. The fantastic Arb library uses this, and sort of something that we thought might be good to check out at some point is seeing how interfacing, how that affects speed. But for us, it was easier just to implement everything in Sage, especially with how sort of the error bounds on Arb and using these rectangular regions interface with the actual way that we're going to calculate n. And that way is going to be using this fact that we know that for our Riemann surfaces, these differentials are actually going to be algebraic, or there exists a way to have them algebraic, and so it's going to have a minimal polynomial. We can then use Fujiwara's bound to get a bound on the roots of this polynomial in terms of its coefficients, and you know we still have that the a naught depend on z, but if we actually expand these a naught, which are going to be polynomials on some circles, you do a little bit about messing around with expansions, it turns out that you can get a genuine bound on M completely from this minimal polynomial and the data that's contained there. So we can go back to our error bound, we can compute an exact value of n to get any error that we want, And this means that rather than having to go through this process of doubling n and doubling n and doubling n, we can calculate n. It's a little bit of overhead to that, but then we can do this integral in one, which is brilliant for us. So that's that again. You know, I'm speaking quite fast, and I hope you're holding on. But hopefully, that's the first part of my summer of code work, was implementing this rigorous way of making these Gauss-Legendre integrations faster. And that was going to be important because we're going to do lots of these Gauss-Legendre integrations when calculating the Arbol Jacobi map. So we better hope that we've made that as good as possible to start with. So there are a couple of tickets there, and that's now all been merged into Sage. So as I mentioned, there's some sort of process with ellipses and circles. And just to give you sort of a brief picture, this is what's going on. We've got some segment -1 to 1. We end up splitting it up, and we won't actually have time today to talk about all the different ways that, you know, there are decisions on these circles, these ellipses, there's splitting, and that'll hopefully be the content of our paper. And it's probably also worth saying just briefly, we say rigorous here, not certified, because we're not careful with how sort of floating bits, what happens at the tail end there. So if you do want to do something that's certified, you should go back to Arb. It does all this very well. So the second part that we want to talk about is, you know, the Arbol Jacobi map that we've implemented. We've given a brief overview of its definition. So we want to talk about actually some of the decisions that go into actually implementing this. So we now have integrals on straight line segments. So let's just fix our base point. You know, we mentioned that this was a choice when we had our Arbol Jacobi map. Let's fix it to be a vertex of this Voronoi skeleton. You can always calculate the Arbol Jacobi map with a different base point, just using this simple formula. And so we gave two different methods, one which is this based, which is using this fixed vertex, and then a general Arbol Jacobi method, which allows you to vary that or give any generic divisor actually for the argument. And choosing it to be a vertex of this skeleton turns out to be really, really good, because we're going to start reusing paths of integrals, which are from this Voronoi skeleton. We're going to start reusing graph algorithms to choose a path that we already have all the integrals for. So that's going to be ideal for us. It's going to make us save on a lot of computation. As a part of using all these graph algorithms to choose our path, it means that we don't have control over actually the path that we want. And so our approach was to just say, ignore it. You get one vector out if you calculate the Arbol Jacobi map, but then you want to be able to tell if two vectors are actually the same modulo these vectors that we know come from choosing a different path. So we implemented this method, reduce over period lattice, and that's all it does. It takes one vector, another vector, subtracts them, and see if it's small in your lattice. So that's sort of useful, and that solves this path problem. It might be something that we want to go back in the future to choose different ways to do paths. We'll talk about that in a minute. Now, if our point P is not on our skeleton, we can just go to the nearest vertex, as I said, and use this path algorithm. That's going to work well. We are going to have some places, though, where this isn't going to work. So, as I said, for generic P, this works well. But if our point P is at infinity, which we know we want to be able to consider, for example, I told you about the Arbol Jacobi map based at infinity for an elliptic curve. I said that that was something we want to care about. Then we know that we actually have a singularity at one endpoint. So we can't now use this rigorous bound, because we can't actually say that we've got holomorphicity on any ellipse, or at least any ellipse that isn't just the segment itself. So this isn't going to work using our rigorous integration. Also, if we want to go into a ramification point, the way that we actually end up doing these integrals, we evaluate at a node, we calculate the W, and the method that works in Sage just certifies multiple continuation to calculate that W. And if we've got ramification, you know, we've got two sheets coming together, the actual difference between those two values of W, or these n values of W, becomes harder and harder to discern. So we're going to need something else to do here. And effectively, the answer that we came up with was cheat and not do anything smart. So what we did was use double exponential integration. This turns your finite region, -1 to 1 that you're integrating over, to a doubly infinite region. And we use a different set of weights of nodes. And we can then go actually use, in the same way that previously was implemented in Gauss-Legendre, just double up n, heuristically get the error bound. And that goes on underneath in the background of our Arbol Jacobi implementation when you go into one of these nasty points. And this goes in this method, integrate differentials iteratively. This isn't a great method, to be totally frank with you. You know, it's not rigorous. We don't have an error bound. It might take sort of really long, and we have no sort of assurance that we're actually getting a right answer because it's only a heuristic error bound. So we want to do something better, and there'll be future plans which we'll discuss about how to improve going into these points. But for now, what you can do is just stick to rigorous integration and use what's called strong approximation. So this was an algorithm that was defined by Florian Hess, implemented in Nora's thesis. So I should say a lot of these ideas have been used and adapted from Christian Neura's thesis, which does this work in Magma, but obviously we wanted an open source implementation. And this just says if you want a divisor to do this integral up to, this method, strong approximation, can give you another divisor that this tilde symbol is saying equivalent. And for our purposes, we can just say that equivalence means they have the same Arbol Jacobi map, which is great for us. And we can say that it avoids a set of places S. We can find an equivalent divisor that avoids some set of bad places. And so practically what we end up doing is sort of taking S to be the places at infinity and the places at this branch locus. The places, we've said there are problems with either singularities or, inability to discern points. And because of this, method uses function fields and sort of that backends that are inside Sage, this also currently requires the base field to just be Q. But again, this was implemented in Magma, and there's no restriction there in Magma because this can use algebraic fields. So that's something we'd like to look at in the future. Now, this was the content of one large ticket, 32297. This is something that's not been merged yet, and we'll talk a little bit about that in a minute. So once again, I've spoken very, very fast and spoke a little bit about the implementation. If anyone has any questions on that, please do let me know.
What kind of values of the genus are you using for examples, and do you need for your applications? How big is the genus?
I personally, I think I've only ever gone up to genus 4. That's what I'm, so something else that one of the applications that I'll talk about is a paper that I'm writing with my supervisor, Harry Braden, right now. We're doing this on Brings curve, so that's genus 4. And this works absolutely fine for that. We're certainly right to question this, that I think higher genus will start running into problems. But I think from my understanding, if I recall, Niels in his paper that I mentioned, BSZ, I think checks a genus 17 curve for this calculation of the period matrix, and I think it works quite well there.
Was that hyperelliptic?
I don't recall, I must admit.
Do you have special code for the hyperelliptic case, which might be simpler in various respects? Or?
So this is a great point, which I was hoping we can talk about. We don't yet, but Shaska has done implementations for superelliptic curves, which use specific integration schemes, which do take advantage of that. And so you're totally right to ask that there is benefits to be found when we know more structure about the curve, but we've really given quite a generic, but quite malleable system that works very well, we've seen.
Okay, thanks. I'll let you continue.
No, it's great. And if anyone has any more questions, do let me know. But otherwise, we'll just speak quickly, as I said, about the applications and then sort of what we might hope to do in the future. So sort of on a very sort of basic level, making this rigorous integration means that we can do a lot more higher precision calculation for higher genus curves. So, I mentioned back at the beginning and sort of haven't discussed it yet that we need a numerical precision because we're doing this Gauss-Legendre, everything is numerical. But you might be, certainly as Niels is, number theorist or enumerative geometry, and you want to know about things that are rigorous. And so in practice, the way one might do that is set a precision and keep going higher and higher and higher precision and checking that these things actually end up working out. Because none of these algorithms are only, as we said, certified. There is just hopefully some sense which you choose a big enough precision that it all works out. And in that sense, we just want to make these calculations as fast as possible to allow you to probe higher precision. Now, also, as I said, I'm a mathematical physicist, you might just want to use these for actual mathematical physics and integral systems applications. So using the theta function, which is related to this inversion, you can calculate solutions to PDEs, such as the quarter-vector-Riesz equation. You can calculate the Riemann constant vector, which is related to these theta solutions and related to, understanding spin structures and theta characteristics, which is also something that we're working on right now. So that's very useful. And indeed, that sort of plays into a wider story of string theory. On a much sort of lower level, classical integral systems getting actual angle coordinates is really helpful. It's something that we want to do. It allows you to understand that dynamical system in a very concrete sense. And to do that, you just need to do the Arbol Jacobi map. There's no extra tools. You're just doing integrations of differentials. And so we hope that, and this is something that we've not implemented yet, but want to do, is actually calculate action angle coordinate on a bunch of different systems to see if we can learn a bit more about them. Also, as we mentioned, you can actually just use this to check divisor identities, compute isogenies, and these are tools that we've used again. So this Arbol Jacobi map need not have a specific implementation in mind, sort of be a tool in your toolbox to help you aid in discovery. And yeah, I sort of finally say, Mabel can do lots of these things. So Mabel has an implementation of the Arbol Jacobi map. Magma has an implementation of the Arbol Jacobi map, but we want something that's open source and we can get our hands dirty with. So yeah, what's the outlook? Where are we going with this? What's the next stage? As I said, this ticket so far has not been merged. So hopefully you'll have all been deeply inspired by me talking today. You'll all find it incredibly exciting. You're going to go out, you're going to look at this ticket, you're going to tell me what's wrong with it, and we're going to fix it. Because certainly, as I've said, we know that going out to these points of infinity and these branch points, we're using this method that isn't great right now. We sort of know that, so if we can make that better and we can understand what's going wrong with it, that would be perfect. So one of these attempts might be to use GSoC series. So that's what goes on right now in Maple. You can calculate effectively what's a Taylor series, but in sort of a fractional exponent. And so you can end up actually doing these integrals as successive, sums of integrals of things which we know the exponent of. So that's sort of one approach that we might want to use. We also, as I've said, have multiple times seen the restriction that comes from our base field. So with strong approximation, it needs to be Q. Anyway, regardless, it needs to be an algebraic base field if it's going to be in Sage. But not all spectral curves and not all Riemann surfaces have that. So here's one for a monopole, which is something that I carried out. It's got that beta function in there. That's transcendental. So we need to do something. And so we might want to look at interfacing with libraries which know how to do this. So for example, I know that Frederick Johansson's Calcium is meant to be very good at dealing with transcendental fields. And so perhaps that's something to look at working with. Finally, a sort of an extra thing, we mentioned that we're forced to a homology choice by this Voronoi decomposition. And that's okay. This is a really good decomposition to get your homology basis from. But often when you're doing sort of actual number theory and you don't just want numerical answers, you want to choose a homology basis that is somehow adapted to the symmetry of your problem. And for previous implementation in Sage, so something I should say is that work was done well before 5 years ago by Christian Swirsky, which implemented what was called Arbol functions in Sage. And this had a sort of a tool as well in it called Cycle Painter, which could be allowed to construct your own homology basis. Those unfortunately have become a bit old now and aren't very usable. I tried to use them in sort of this recent paper that we're working on to get comparison, and I couldn't even get it to work, which might just tell you that I'm very bad at coding, or might tell you that we need something that's more up to date. But regardless, we might want something that can tell us this intersection with different homology bases, so we can get a sort of better picture of what's going on with our curves. So with that, thanks very much for listening, and yeah, let me know if you have any more questions.
Thank you very much for the presentation. I have to admit I'm not very familiar with algebraic geometry, but everything in your presentation looks really exciting. Do you have any questions for the speaker?
Well, I have another question, but I don't wish to jump in if anybody else wants to go first.
Please go ahead.
Okay. So for elliptic curves, I need the genus 1K, and to some extent for, I think, genus 2 and maybe 3 in the hyperelliptic case, there are methods of computing this using the arithmetic geometric mean. I don't know if you've come across those. It's certainly...
but certainly, I should, yeah, sorry, I'll let you finish, but certainly for the elliptic case.
It's quite simple in the genus 1 case. Maybe I'm only saying that because I understand that case very well, and I've implemented that in Sage. For the genus 2 and 3, it gets more complicated, but there are people who've worked on this. And obviously, it's great to have something completely general, as you're doing, but it might be useful for checking, because you might, if you have a different way of computing the same numbers, you might find that useful. Certainly, if you wanted to test your code in genus 1, then you could look. So that's sort of buried in the elliptic curves part of Sage.
Yeah, that's brilliant. I do know that's there, so that would be excellent. And certainly, I think folding that in, because I think my understanding is that it gives you very quick convergence in the elliptic.
Well, yes,
case.
that's the brilliant thing about it. You don't sort of obviously do any integration at all. You have an iteration which doubles the number of digits of precision with every iteration. So it's,
yeah, no, that's perfect. That's been implemented. Do you know where in the elliptic curves section?
yes. Why don't you contact me?
Sounds perfect.
You can see my name on screen, because I mean I wrote that, and I wrote a paper about it, so it works over with complex input, not just real input, and so on.
Perfect.
If you
No,
contact
that
me
sounds
about
brilliant.
it, I'll be happy to give you some pointers. Thanks for a great talk.
No, thank you.
Excellent. Let's thank the speaker again. And I'm just wondering, you're going to be around in like 1 hour, 1 hour and a half. Although I don't know the technical details, I do have some non-technical questions about Sage experience, Sage GSoC experience to ask you.
Yeah, no, I'll be about.
Okay, great. All right. Then let's welcome our second speaker, David Ayotte. Ayotte, are you there?
Yeah, hello. Hi.
Did I make you co-host? Yes.
Yeah, I will share my screen.
Excellent.
I can. Oh. Oops. Can I see my screen?
Yes. Maybe you would like to make it full screen?
Yeah, that's what I want to do. Like this. Okay.
Okay. David Ayotte is going to talk about the implementation of graded range of quasi-modular forms as his project of GSoC 2021. Please go ahead.
Hello, everybody. So today the goal of my talk is to explain my Google Summer of Code 2021 project, which is on the implementation of the graded ring of Quasimodular forms. I was mentored by Vincent Delacroix, who is an active SageMath developer. For those who don't know me, I'm a PhD student at Concordia University in Montreal. And I've been greatly interested in modular forms and their generalization. So obviously I was really glad to participate in a project related with modular forms. For those who don't know modular forms or quasi-modular form, don't worry, I will give a quick recap. Okay. So my talk is basically divided in two parts. The first part is an explanation of the theory and the general ideas of the implementation. And the second part is a Jupyter notebook that I've prepared, so we can see the implementation in action. Okay, so what are modular forms? Consider H to be the complex upper half plane. We define an action of SL2Z, which is the group of 2x2 matrices with integer coefficient and determinant 1. We define the action via Mobius transformation, like so. Definition: a modular form of weight K for SL2Z is an anamorphic function f from H to C such that we have this invariance relation for every gamma in SL2Z. This is what we call the modularity condition. And notice that this condition, if we replace gamma by 1, the matrix 1, 1, 0, 1, this relation becomes f of z plus 1 equal f of z. In particular, f is an holomorphic function. It's a periodic function, sorry. And so we can, it admits a Fourier expansion. So the second condition for f to be a modular form is that this Fourier expansion is of this form. In particular, that In other words, there's no negative power of n in the expansion. And this is what we call the Q expansion of our modular form. And this property is called the holomorphic. We also say that F is holomorphic at infinity. Okay, and we'll use this notation to denote the space of modular form, M sub K. And an important fact about this space, it's a fact, it's a not so trivial fact to prove, is that this space is a finite C vector space. This is important for computational purpose. And in SageMath, there are already it's already possible to create the space of with K modular form and compute their dimension. We can also compute basis of this space. So it's very useful. Another useful fact is that this Q expansion determines our modular form. And there exists also a bound named the Stern bound that tells you that you only need a finite number of coefficients to determine its Q expansion. So this is also useful for computational purpose. Okay, so now let's talk about a very important example. Take K to be K greater or equal to 4, an even integer. The weight K Eisenstein series is defined by this sum. This sum is absolutely and uniformly convergent for every Z in the upper half plane. The fact that it is absolutely convergent implies that it does not matter, the order of summation does not matter. In particular, this implies that we have the modularity condition. And we can also explicitly compute the Q expansion of this function. It is given by this beautiful formula, which involves the Riemann zeta function evaluated at K, and these arithmetic function to sigma K minus 1 of n, which is the sum of all the K minus 1 power of the divisor of n. For computational purpose, it's useful to normalize it so that we have only integer coefficient. And we will consider EK for the rest of the talk. And why did I say it's a very important example? Because we have this result. We have an isomorphism of graded C algebra given by this. So the ring of, this is what we call the ring of modular form, this direct sum of over all the weights. It is isomorphic to this polynomial, this space. Basically, this ring is generated only by two forms, E4 and E6. So the weight 4 and the weight 6 Eisenstein series generate all the other modular forms. So this object was already implemented in SageMath when I started my project, but we had to do some very important changes to the code, and I will explain them later. Okay, so now let's move on to a special case of an Eisenstein series. So before I suppose that K was greater or equal to 4, this tells us that this sum is absolutely and uniformly convergent. But what if we take K equal to 2? We can do this, but in this case, we lose the absolutely convergence. So we need to choose a specific ordering of the sum, which we do like so. But this choice of ordering gives us this Q expansion, which is very similar to the one above. But since we lost the absolutely convergence, the absolute convergence, we lose also the modularity condition. It becomes this relation instead. So we have this little annoying factor that appears. So it's really close of being a modular form. It's so close to being a modular form that we call it a quasi-modular form. So what's a quasi-modular form? We consider the set of holomorphic function which admits a Q expansion. Definition: an holomorphic function f from H to C is said to be a quasi-modular form of weight k and depth at most p for SL2Z if f admits a Q expansion and if there exists holomorphic function f0 to fp such that we have this relation for every gamma in SL2Z. So basically this function should be a polynomial in C over CZ plus D of degree at most p with coefficient in these functions. So by definition, the weight 2 Eisenstein series is a quasi-modular form. And we use this notation to denote the space of a quasi-modular form. If we don't care really about the weight, we only added the depth, we only take the union here. So next I want to introduce the space that I implemented in SageMath, which is the graded ring of quasi-modular form. So we have seen before that the ring of modular form is generated by E4 and E6. So what about the ring of quasi-modular form? In fact, we have a really similar result, which is basically we only need to add the E2, the weight 2 Eisenstein series. So it's generated by three elements. In particular, the graded ring of quasi-modular form is generated by E2 over the ring of modular form. So this proposition is the base of the SageMath implementation. So the SageMath implementation was made basically in 2 steps. The first step was to make the class modular form ring into an actual ring in SageMath. So a modular form ring, this is the class that was already implemented in SageMath, but it was not an actual ring. And the second step was to implement the ring of quasi-modular forms. So let me elaborate a little bit more about the first step. Before this project, that is in SageMath 9.4 and before, the class modular form ring was only inheriting from the generic class Sage object. So this is a really generic class. Basically, any object that is returned to the user in SageMath inherits from this class. So it's not very useful. So now we implemented the parent element framework for this class. And we also implemented the category framework for it. It is now a graded algebra over a ring. And moreover, we implemented an element class for a modular form ring, which is named graded modular form element. So basically, we can now take two graded modular form and we can sum them, we can add them, we can even multiply them by a scalar. So so what's a graded modular form in Sage? In short, a graded modular form is simply represented by a dictionary like so, where the keys are the weight and the values are the modular form. And so this dictionary represents this sum basically of modular forms. So one needs to be really careful here because a sum of a modular form is not a modular form in general. Because if you take two weight 4 and a weight 6 modular form and you sum them, you get a function, but it will not be a modular form anymore. It will be an element in the ring of modular form. Okay. And finally, the graded ring of quasimodular form in Sage. We implemented a new class, basically quasimodular forms, with a new element class, Quasimodular forms element. And let's recall that we have this isomorphism. And so graded Quasimodular form H is simply a polynomial in E2, where each Fi are graded modular forms. So now that the ring of modular form in SageMath is an actual ring in SageMath, we can now consider the polynomial ring over this ring of modular, and we can consider elements of this form. So I think that it's time for my demo. Yes. Let me share. I will share another screen. Share. Oops. Do you all see my screen? Is the writing is not too small? Okay. So let's start. So this command simply initialize the modular form ring for SL2Z, and we can ask for its number of generator like this. We as expected, we have 2 generator, and let's initialize these generator. So this is new. Before this project, it was not possible to access a generator by writing just m.0, m.1. So this is new. So this is simply to illustrate that we now have really a parent element structure in this new ring. We have a class, we have an element class, and the parent of E4 is a ring of modular form for modular group SL2Z over rational field. We can now sum 2 modular form like this. And now I want to illustrate again that, stress again that the sum of 2 modular form is not a modular form. So we can verify this with SageMath too. For example, I summed E4 and E6 here, but E4 and E6 is not a E4 plus E6 is not a modular form. So we can verify this by simply checking f dot is homogeneous, or same as f dot is modular form. Return false. If you ask for the weight of this graded form, it will simply return you an error because it's not a modular form. You can ask for all the weights component of a modular form. For example, here f was the sum of a weight 4 and a weight 6 component. So now you you can access all its weight, and you can access its weight 4 component, for example, just like a dictionary like this. This will give you the weight 4 component or the weight 6, just like this also. So now how do we, if we want to create a graded modular form, we can do it via a list or simply a dictionary and use the element constructor of the method. For example, I initialize 2 modular form. These are not modular form in the ring of modular form. They are modular form in the space of weight 4 and the weight 6 modular form. But to initialize, I just simply use the element constructor of this list and or this dictionary, and it should give you the same element. Okay, so also we implemented conversions. So for example, take everybody's favorite weight 12 Quasimodular modular form. You can this modular form, its parent, you see, it's not a modular form ring, it's a modular form space of weight 12. So but if I want to see it as an element in the modular form ring, I can write M, use this structure, and it will be now an element in the ring of modular form. And if I want to do some computation involving a graded modular form and a modular form space element, then it's still possible. We have the conversion will be taken care of. And as I said before, we have a lot. We can verify if, for example, here I took an example where this graded modular form is really a modular form. We can verify it. This is true. This we can compute its weight and ask for its parent again. Okay, and another feature that was implemented was the push out. If you have two modular form living in a different space, we have one here living in a weight 4 space and then other living in a weight 6 space. We can sum them, and the result will be an element in the ring of modular form, like so. E4 plus E6, the result lives in the ring of modular form. So this before this project would return you simply an error. Okay, another cool feature that was implemented, we now have polynomial conversions from generator. So here we'll take a little bit different example. I took the modular form ring, but for some congruent subgroup. I didn't talk about them in my slide before, but we can consider a subgroup of SL2Z, certain subgroup of SL2Z, and consider modular form for these subgroups. So in general, we will have bigger space because we consider a less restrictive subgroup. So for example, let's consider the ring of modular form for gamma 03. So here, instead of 3 generator, we'll have instead of 2 generator, we will have 3 generator. But here we should be careful here because it's not we can have a polynomial. We can have relation between the generator. So that's why I wrote this quotient here. So yeah, we can have polynomial relations. Okay. And now I name these 3 generators and I consider a random modular form here, defined like so. So if I want to convert this modular form into a polynomial in terms of this generator, you can simply write f.to polynomial with the names here. Each name will correspond to a generator of the space. So doing this, it returns me a polynomial where z corresponds to this z, and x this corresponds to this x, and y to this y. And so this polynomial corresponds to the relations that we have. But here, observe that this polynomial is different from this relation that I wrote here. This illustrates the fact that we have a quotient here. So we have indeed some relations between the generators. But we can verify that we indeed have the same modular form like so. We can use the element constructor and just use a polynomial here, and it gives the same modular form.
And this again illustrates that if you start with a polynomial, you can construct a modular form. If you are but you need to know the number of generator of your space before. And each generator of your polynomial ring will correspond to one generator of your graded modular form ring. Okay, so most of these features that I talked are also implemented in the graded quasi-modular form ring because because they are really similar. So I won't explain them all again. So we can create a quasi-modular form like so for SL2Z. This you can ask for the polygen here. This will return you the E2, but E2 as a univariate polynomial ring in E2 over the ring of modular form for modular group SL2Z over rational field. So this E2 is a generator for this univariate polynomial ring. You can ask for the generators. So here, this is the weight 2 Eisenstein series. This is the weight 4, and this is the weight 6. If you only want the weight 2, you can also find it like using this method. And I think I'm gonna skip this one. I'm running low on time. Yeah, this was a new feature that we implemented too. If you take a modular form f of weight k for SL2Z with a certain q expansion, in general, its derivative will not be a modular form, but it will be a quasi-modular form. So we implemented the derivative of modular form. For example, if you take the derivative of E4, then it will be this form with E2 that appear. This, but we basically use this theorem. If f is a modular form of weight k, then this theta of f defined as such is a modular form of weight k plus 2. So this is what we call the Serre derivative. Here's some computation of the Serre derivative. For example, take the d defined like this, and you can compute the Serre derivative of E4 also. And you see E4 was a modular form in a space of weight 4, but its Serre derivative returned a modular form in the weight 6. So it raised its weight by 2. And we can compute here the derivative of a modular form. So here the Serre derivative was this form, this form, but the derivative is the q times d over dq. That's the derivative. Yeah. But this is not implemented on the weight k modular form space, I guess. I think that it could be done. So something for the future. And let's do some verification here. It's a ring of modular form. It's not a modular form. And it's not a graded modular form also. So it's really a quasi-modular form. And you can convert this derivative to a polynomial, just like we did before. And this is indeed what I wrote in my example here. So everything works. We also have conversions. For example, here I'm doing some computation with a graded modular form, a quasi-modular form, and an element in a modular form space. And it will return you an element in the quasi-modular form. space, ring of Quasimodular form. So yeah, I'm finishing some further development that could be done. Maybe implement the spaces of a Quasimodular form of fixed weight. This could be done because we have spaces of fixed weight for modular form. Another point would be to I'm currently working on this. Is make the gens form method return graded modular form ring element. Let me explain this. So here I have m dot gens form. This returns the generator of this space, but the element returned here are not graded modular form. They are space modular form space element. So I think it would be better for if it were modular form ring element, but I'm still thinking about this because there are some issue with the base ring that happened. And maybe another point I was thinking is to revisit the generator finding algorithms for modular form rings, because these were written, I think, some times ago, and I think there was some progress that was made, but I didn't investigate too much this this subject, but I guess one could check this in the future. And that's all for my talk. Thank you for listening.
Okay, thank you very much. It was very interesting. Do we have a quick question? Okay.
Yeah, I perhaps wonder if that's all right.
Yeah.
So just in terms of these modular forms that we've been seeing, they've been sort of truncated series. You know, they've gone up to q to the 5 and then given an order q6. When these are implemented, do they only contain up to 5? Do they have a generating series for these AN that you'd written down? What is sort of behind these?
Okay, well, in SageMath, a modular form is basically a vector, where this vector is represent because mk. Let me do some. It was 112, for example. This M is a vector space of okay, it's a vector space of dimension 2, so we can ask for basis. So a modular form for this space will be represented by a vector where each coordinate is simply represented is on the basis of this vector. Yeah. What I want to say is that we know the Q expansion. We just compute them when we do the representation, or you can ask for the representation, but you don't store the Q expansion necessarily.
So there's a closed form for if I wanted, for E4 to ask for the coefficient of Q27, you could spit out that number for.
Yeah, for example, in my slide before, I wrote the Q expansion for the Eisenstein series. We know its Q expansion, so we can compute them as much as you want, and it's basically this that we use. Yeah.
Thank you. I do have some questions, maybe silly questions about category, but in the interest of time, I will ask you afterward, after the next talk.
Yeah.
You're going to be here around. Okay, great. Yeah. So let's hand the floor to our next speaker, Trevor. Could you share the screen?
Yeah. Can you see that okay?
Excellent. Okay, our third speaker of this session is Trevor Kahn from University of Minnesota. He's going to talk about GSoC 2021 project on invariant algebra. Please go ahead.
Awesome. Thank you so much. And thank you so much for organizing this session. And thank you to Matthias and Jean-Philippe as well for organizing these Sage days. I'm going to talk about my project from last summer, and I was fortunate to be mentored by my PhD advisor, Vic Reiner, at the University of Minnesota, and then also, if you were around for the prize ceremony earlier, I think Travis definitely deserves that prize. He helped me out mentoring me last summer as well, and I learned a lot from him. So I agree with that winning of the prize. And then if you want to see everything we've done, there's a meta ticket at the track 31929. So if you want to see more details, you could definitely check out that. I'm glad to see that we're all sort of following the same formula of starting talking about math and then going through some code and examples. So I will continue that trend. Okay, so I'm going to think about a finite group G and a finite dimensional associative algebra over a commutative ring. Those are going to be my two stories. I'm going to sometimes forget about the algebra structure of A and just think of it as an R module, but I'll try to be clear about when I'm thinking about it as an algebra and when I'm thinking about just the module structure. Okay, so we're going to equip A with a G action defined on some generating set, and that should extend multiplicatively and linearly. So everything should be sort of as nice as possible. You know, maybe there's something to check that the action makes sense on the and it actually extends multiplicatively. Our Sage implementation will not check that for you, so you should be careful that your action makes mathematical sense. And then we're going to define the G invariant subalgebra of A to be exactly those elements of A which are fixed under the group action for every element of the group. In general, these are not going to be generators. If you just send every generator to itself, that would be maybe one example, but that's sort of a boring action. So we want to think about things that are maybe a little more interesting. And we'll denote that invariant algebra by a superscript G. Maybe I should just convince you some reasons to care about these things. This is sort of slightly different setting from what I've said for a finite dimensional algebra, but one example you could think of is the symmetric group acting on polynomials and variables, where the action is just permute the indices of the variables. In that case, the invariants are going to be symmetric functions. These are also implemented well in Sage, and I'm not trying to supersede that implementation. If you want to think about symmetric functions, you should use that implementation. It's really well developed. It's great. But you know, if you want to think about maybe a more general ring or a different action, that would be the setting where you'd want to use the things we've developed. If you're looking for a mathematical reference, that's in Stanley's Enumerative Combinatorics, Volume 2, Chapter 7. I think I'm required to say that that is the reference. Okay. Another example you might care about is if you have a topological space X, and A is going to be your cohomology of that space. When G is acting on your space, that induces an action on the cohomology. And in that case, the invariant ring is the cohomology of the quotients of the, the orbit space. So in the orbit space, you identify all points that are in a common G orbit. And then it sort of makes sense that the invariant should be the thing, excuse me, the invariant should be the cohomology of that because you want two things. You want the cohomology of the quotient space to be related to the original space, to the cohomology of the original space. But you also want the G action to be trivial because you've already identified all points in a common orbit. So if I hit anything in X mod G with G, that should fix it. And so the invariant algebra is maybe a candidate, and it turns out that that's the right thing. It's fixed under the action, and it's related to the original cohomology. Oh yeah, I'm sorry. And if you want to look at the details of that, you can look at Hatcher's algebraic topology, the section on transfer homomorphisms. Okay. This is also can be viewed as a representation. We're going to view A as carrying a representation of the group G. And the way that I like to think of it, at least, is as a permutation representation on a basis for A. In this case, AG is the largest submodule of A, which carries a trivial representation. In particular, this is not always necessarily one-dimensional. It could be zero-dimensional if there's no copies of the trivial representation in there. Or it could be the entire thing if G acts trivially on A. So I just say that to say it's not just one singular copy, it's the entire, everything in there that is a copy of the trivial representation. But it is more than just that, because it does also have an algebra structure. If you multiply things and act trivial, and they're fixed under the group action, it shouldn't matter whether you multiply them first or whether you act, everything will be fixed. And so this maintains an algebra structure. And I'll say a little bit more about that later. So we could think about the trivial representation, and we could also think about maybe a more general irreducible character. So I'm going to let chi be my favorite irreducible character of G. I should say that in the Sage implementation of all of this, we don't have any checks that chi should be irreducible. So we're trusting you to give an actual irreducible character. Things might go awry if you pass a or if you pass a irreducible character. Okay, and then so just like we had this isotypic component of the trivial representation, the biggest space that corresponded to the trivial representation, we can also have this isotypic component for any irreducible character. And we're going to denote that by AG chi. So this is the part of A that looks like chi, or maybe a direct sum of a bunch of copies of chi. And AG chi it's going to be an R module just naturally, but then it also turns out that this is a AG module, and that's something I'd like to implement in the future, is the correct coercion between AG and AG chi, so that it understands, so that Sage understands that module structure is good. Okay, so everything I've talked about so far has been for a pretty general setting. I also want to dig in more specifically to sort of the motivating example for this for me. There's these Orlik-Solomon type algebras, and there's so many different ways to define it. I couldn't pick one, so I'm giving you sort of many different ways to think about this without giving you any actual formal definitions. I think the way that I came to it was as the cohomology ring of the configuration space of n many points in R to the D. If you're familiar with like the Orlik-Solomon algebra, that would be D is 2, but there's a more general story with the Varchenko-Belfond ring that is for arbitrary D, and so that's the setting I'll use here. And if you're also familiar with the usual Orlik-Solomon algebra, that's going to be the cohomology of the complement of a hyperplane arrangement. So the hyperplane arrangement is telling you where your points cannot lie in the configuration space, but I guess the way Orlik-Solomon thought about it was for a hyperplane arrangement. I could also just tell you that this is, if I have some matroid M, this is some algebra that I've associated to it, and I can tell you the basis. The basis is consists of these things called no broken circuit sets. I won't define exactly what a broken circuit is, but it's something that has to do with the dependence relationships within a configuration of vectors, and also the order on those. And so if I have a set that can contain a broken circuit or it cannot, if it does not, we'll call that a no broken circuit set. That is the basis for these Orlik-Solomon type algebras. Maybe the multiplication relations will change depending on how D changes, but in general, we'll look at things that have a no broken circuit basis. Okay. So let's try to get into some code now. Here, I think, are the things that I would like to say. These are my contributions from last summer. So we included a category option for the existing representation class. This is maybe a sort of minor contribution in terms of lines of code, but allows a lot more flexibility in the use. Also implemented the invariant algebra and invariant module, this twisted invariant module. So this would be the one corresponding to the trivial representation, and then this is the one corresponding to your favorite irreducible character. And then also implemented an existing algorithm from the literature to speed up computing the no broken circuit sets, which in turn allows us to compute the basis for the Orlik-Solomon algebra much faster. Okay, so let's talk about categories for the representation class. So here I'm going to import the category of algebras, and I'm going to also import this representation class. So what representation does is it takes a module with a specified basis and some group action, and it understands that to be a representation. So I'm going to pick G to be the cyclic group of order 3. So you could think maybe rotations of a triangle, Z mod 3Z, however you like to think of it. And then I'm going to think of my algebra A as the exterior algebra generated by with 3 generators. And so what this is going to look like is all subsets of 3 as a basis. The rules for multiplication are that x times y should be negative y times x. So it's almost commutative, but not quite. And so in particular, this forces that x squared should be negative x squared. So x squared is going to be 0. That's just saying, okay, it'll be finite dimensional. Here's something that I didn't learn until after the summer, so I wanted to make sure to say it in case it's helpful for anyone else. If you call this inject variables method, you can then just use the generators. You don't have to call a ngens method and assign things to new variable names. Maybe you all knew about that, but just in case you didn't, that's something that I've found helpful. Okay. And then we should also define this Z mod 3Z action on A. So I'm going to do that by defining a lambda function. And the inputs are going to be G, which is going to be a group element, and A, which is going to be an algebra element. So this is currently acting on the left. We do have a way to act on the right if that's something you need. In which case you would just swap those. Okay, so I'm extending this multiplicatively, and I'm just saying, okay, well, this should be permuting the variables. So in the same way that we saw symmetric functions earlier, this is just that same action on the subscripts. Okay, and then I'll go ahead and define a representation here. And for now, I'm going to leave out the category option. This would be the existing behavior before last summer. Okay, so go ahead and execute that cell. So now we have x0, x1, x2 in our namespace. And I'm going to define G to be the 3 cycle 1, 2, 3. So this is a generator for G. In terms of A, it's going to send x0 to x1 to x2 to x0 and so on. So let's just check. If I send x0 to x1, x1 to x2, and x2 to x0, well, that should fix this element. So let's just double check. Okay, great. So we see that G acts on this element by sending it to itself. So this is an example of an element in AG. Okay, so now let's see what happens to x1 times x2. So it's going to send x1 to x2 and x2 to x0. But now this is out of order because I have x2 times x0. So I should sort that into order to put it in the express it in the correct basis. And that's going to pick up a negative sign. So I should act on x here by sending it to negative x0, x2. So if we go ahead and check, that's exactly what we get. This is a little bit of a contrived example. It might become more clear later why I would want this, but maybe I'm already thinking of things in the representation. And I'd like to be able to multiply them. That is how we should think of this if we're really thinking of the algebra structure. So, I mentioned before that it's not only just a copy of the trivial representation, but it is, or many copies of the trivial representation. It's also got some algebra structure. And right now, if you go ahead, that throws an error. So what we can do instead is we can add this category keyword argument. So we're saying it's in the category of algebras with a distinguished basis that is also finite dimensional. And now I can go ahead and say x is going to be rx1 times x2. So that's the same, like mathematically it's the same element as before, but now it's understood as an algebra. And we can check, excuse me, x, g times x, g squared times x turns out to be everything that you want. Okay, so now I'll talk a little bit about the invariant algebras and invariant modules. So right now, our representation R is going to be considered as an algebra. So the invariant module here, that was maybe a choice for the general setting, but because we passed the keyword argument, we know implicitly that this is not just a module, but actually an algebra. So this is a method we added, and it will go ahead and compute the invariant algebra. In particular, I can find a basis for it. So now I know a little bit better how to work with it. Sage will go ahead and re-index this basis. So it's a little simpler to look at. And we can even multiply B1 times B2. And we see that that's 3B3. Great. And just a reminder that anything squared should be 0. But it's also not super helpful to just stare at these B's, because maybe I want to actually understand what these look like in my original algebra. And so I'm going to go ahead and call the lift method on those to see what they are. Okay. So we saw x0, x1, x2. That was the first example of something that was in the invariant algebra. And then here we also have x0, x1 minus x0, x2 plus x1, x2. On the previous slide, that was the sum over the whole group, the sum over the orbit of x here. Okay, and then B3, which we didn't see before, is just x0, x1, x2. You might be worried that if I cyclically permute things, something goes weird with the signs, but I promise it doesn't. It is an element of the invariant algebra there. Okay, I want to do another example. So here I'll take M to be a combinatorial free module over Q. And I'll have the symmetric group act by permuting the vectors. So this is the defining representation. If you write this out as matrix, this is all like 0, 1 matrices with 1 in every row and column and only 1 in every row and every column. Okay. Now it's known that there is one 2-dimensional irreducible representation of S3. And so I can define that using the class function. So this is going to be a function on the conjugacy classes of G. And these are going to be their character values. Again, the class function doesn't necessarily know that this is irreducible. So this is just a general framework, and you have to make sure that you're passing in the right things if you want to really think about an irreducible character. But I'm telling you, this is a good one. Okay. And now I can call this twisted invariant module. So what I'm asking for is give me the subspace of this, which corresponds to this 2-dimensional representation. It is known that this occurs once inside of the defining representation. So you can go ahead and look. And I've got this twist by this character, which is just saying, okay, give me the isotypic component corresponding to this 2-dimensional reducible representation. You can also look at the basis. So that might be how you would want to use it if you're just trying to do the linear algebra. But if you actually want to understand what that looks like in your original module M, you can use the lift method and see that this corresponds to M1 minus M3 and M2 minus M3. Okay. I think I have enough time here to say quickly, well, let me think. Okay, so maybe I'll say quickly how I use this in my own work. Right now I'm looking at trying to understand how the invariants look for young subgroups. So young subgroups are copies of 2 smaller symmetric groups inside of a bigger symmetric group. And I'm going to think of that as acting on a matroid. This is going to induce an action on the Orlik-Solomon algebra. And so all of this is saying, okay, define some matroid. The group I am going to consider is this product of S3 times S1 living inside of S4. The way I want it to act is on the edges of the graph. If you think of the matroid as a graph, it's coming from a graph. I want my action to be on edges. But right now it only knows as a ground set the order. So I'm just somehow associating these edges to the names in the ground set. And then my action says permute vertices. So I have a graph, a complete graph with 4 things, and I act on the vertices by the symmetric group action, restrict that action to S3 cross S1. And then all of this is just saying, okay, rearrange it so that it's acting on the edges instead of the vertices. Okay. Now I can create the Orlik-Solomon algebra for that with coefficients in Q. And one thing we added last summer was this invariant option. So this is saying, find the invariant corresponding to the group G with the action given by vert action. Okay, and I can get a basis for it. Okay, and great, now I have basis. I can also play with it and do some computations in my easier to use index set, right? So this is hard to just look at and understand things about, but once we've re-indexed it, we see that there's some sort of nice relations here. I can express B4 in terms of B1 times B2 minus B3. And I can express B5 in terms of the product of B1 and B3. And so this is a B0, B1 module generated by 1, B2, and B3. Once I have B2 and B3, I can get B4 and B5. Okay, and then just very quickly, just so you know I'm not cheating, I'm going to show you some timings, and I want to make sure that you know I'm not cheating and anything's cached in here. So go ahead and define the complete graphic matroid of a vertex set of size 7. So the original implementation of finding no broken circuit sets was the naive thing to think, which is iterate over all sets and just check, which certainly works. I can go ahead and do that. But it turns out that in 2013, Bishop, Douglas, Verla, and Pfeiffer created a new algorithm which relies on the ordering of the set and is more thoughtful about how to construct these NBC sets rather than enumerating all of them and checking. Bishop, Douglas, Verla, and Pfeiffer find a way to basically construct them. So what we did was we implemented their algorithm and some Python implementation, and this is much faster. So you see it takes about 20 seconds here to find the 5,040 different no broken circuit sets. And again, I'll delete M just so that you know I'm not cheating and nothing's cached here. But if we go ahead and here, there's a pretty significant time savings there, down to 262 milliseconds. Okay, so I think I'm out of time. Thank you so much for coming, and thank you again to the organizers for putting this together. This was really great to hear what other participants did last summer, and I'm hopeful that maybe next year we could have a similar summit like this. Thanks so much.
Thank you very much for the wonderful talk. And thank you all for your contribution last summer. And I hope that you will stay in the community and make much more great developments. Do we have a question for the speaker?
I perhaps have a small implementation question. Just when you were printing these bases of these invariant modules, it seems that rather than giving a list, you're giving a dictionary, which is sort of, key, B of key. I didn't know if there was sort of an important reason for that, if that turns out to be really efficient or something.
That is how the bases were already implemented. I think they're implemented as a finite family. Let me just double check. Yeah, it's a finite family, so a little more than just a dictionary, but a lot of the dictionary.
And what is this being a family, Daniel? I'm afraid I don't know what it is.
Oh, that's a good question. That's a good question. I'm forgetting at the moment. being a general family, it doesn't necessarily need to be finite. And so like you could have a family indexed by Z, which you couldn't write as a dictionary. But I'm forgetting at the moment why a finite family is better than a dictionary.
I think your point about families makes a lot of sense. Cheers.
Trevor, you mentioned the magic method of inject variables. I just want to say, yes, I agree that it's a very useful piece of information. Actually, a while ago, I was working on polynomial, multivariant polynomial, and I didn't know this method until I saw others' code, and I think it's worth mentioning. Also, I noticed that, well, in your talk for algebra, exterior algebra, the base ring, it's always over rational field. The same holds for David talk. So usually it's over rational field, rational ring. I'm wondering if there is a specific reason for the choice of rational field. Is it because it's it's in exact arithmetic, it's related to SL to Z, or otherwise can't be changed to other ring like AA, algebraic field, or anything else?
Yeah, so I won't speak for David, but for myself, I just like the exactness, and I don't want to look at floating point numbers, so I could absolutely do everything here. It just is not so nice to look at when I work over C, but maybe you need that for some reason, and then you could totally use that.
For me, modular form, they are over. For example, I took I defined the Eisenstein series, and I defined them with the coefficient with integer coefficient.
Yeah.
So this allows us to work over Q.
Yeah.
And in fact, we can work over Z, and we can also work over integer modulo P. But
yeah.
The implementation of the modular form ring in SageMath with integer modulo P, there are some issues, and that's why I was talking about this gens form method at the end, because this gens form method, if you create the modular form ring and you call gens form, it will return you modular form, but over the rational number, even if your base ring is integers modulo P. So this is a little bit inconsistent. So I would like to fix that.
So if I want to extend the base ring to, say, algebraic numbers, is there a map or an extension method to do that?
No, no. You mean a map in SageMath?
Yeah, I mean, maybe for your application, it's not so useful because all the coefficients are in Z, and the field is over QQ, and yeah. But I was wondering for this talk, the exterior algebra, well, yeah, just out of curiosity.
Perhaps a question to follow on that for Trevor, if it's all right. You said there that you can use floats if you want. Do you have to worry, or have you seen examples of effectively this finite group action no longer working and not closing if you have this comparison of floats?
I have not seen that, but I almost exclusively work over Q, so that might just be me not being careful enough about that. That's a good question.
Okay, cheers.
Any other questions? Okay, let's thank Trevor again and all three speakers. Great. If I may ask, your experience with Google Summer of Code, how did you come up with the project? Did you write the proposal related to your research topic? I mean, for Linden, I saw that you mentioned the project was started 5 years ago. So I suppose that at that time you were an undergraduate student. Did you already know the topic of research, and you also focused on that topic, and you decided to do a Sage development, or how did you come up with the project?
Yeah, so certainly for myself, you're right. I mean, Niels had implemented this in Sage a few years ago, but I'd never heard of Sage until sort of the start of my PhD, and it was purely because so I showed this this spectral curve for the Nahm's equations, and there's a specific case of that which corresponds to affine Toda, and so I sort of wanted to get the symmetry group for that, so I started using Sage. And then, I wanted the Arbol Jacobi map, and nothing was open source for it. So I sort of had a meeting before I even knew about the Summer of Code with Niels and other people saying, should we sort of choose on a language to start, working on this together in, sort of landed on Sage. And so for me, it was quite convenient that I was sort of planning on spending 2 months of my PhD doing this anyway. And so I sort of at least managed to do it with, some more support, which is good.
How about David and Trevor?
Me, I came across this project on the idea page of the GSoC of SageMath. It was the project was proposed by Vincent Delacroix, and as I said before, I've been interested for a long time about modular forms and everything about them. I've known SageMath since quite some time now, and I've used it in my research for doing computation with modular forms. So I was glad to contribute to this code.
Thank you for sharing your opinion. This is my first year of being as a GSoC Summer of Code mentor, and I was new to the program and still in the learning curve. I was wondering, like your partition of time, your workflow for the summer project, how much time you spend on reading paper and design your code, then actually do the programming, and how much time you spend on testing and documenting. And also, if you want, if I can hear advice from you, what a good mentor should be. Also, if you have advice for new students in this program, what would that be?
I guess that how much time I used, I think the program was 10 hours by a week when I did it, or maybe more, I don't know. I don't recall, but maybe I did that 10 to 15 hours a week, maybe more sometimes. But yeah, for a mentor, I liked when my mentor answered my question, obviously, and to know that he was there and he looked at my work, and yeah, so I like that he was interested in what I did. So yeah, I don't know.
Yeah, I think certainly for me, it was beneficial that Niels had, he's done vastly many Sage tickets, and so sort of had that experience, which was very useful for me, because there's sort of a lot of the things that I benefited from him were also, things about learning that fast callable functions existed, so that can make things run better, or learning about profiling, or yeah, a lot of as a sort of being a mathematician who came to computing, it's useful to have someone who had more of that back end.
Yeah, I think I would also just +1 on everything David and Linden have said. I found it helpful. So I was fortunate to have sort of two mentors, one who had more background in Sage specifically, and then my PhD advisor who had a lot more of the strictly mathematical background. So I don't think I had to spend a ton of time reading many papers because my advisor was able to say, hey, here's the algorithm, like here's the paper, just like go do it now. So that was really helpful for me. And also, I guess one thing that I just want to try to say now is I think last summer it would have been nice to have maybe more communication among the participants. I know sometimes it can be intimidating as a student to go to your mentor for something. You're like, oh no, is this dumb? Should I have figured this out myself? I don't know.
Do you exchange news, or do you talk to each other among your the Sage contributors? Not really. Okay. Maybe it's because the pandemic and everything is online. I think before that, the program is taking place in person. Perhaps we have more chance to meet each other and work together. Okay.
But there is a channel on the Zulip page, which hopefully everyone's familiar with. I want to just say maybe we can use that this summer. I'll be participating again.
There's also the Google group, a Google chat group, like, but I don't see it active recently, so I don't know if you are.
Yeah.
Do you feel there is enough community support for your project?
I think I would probably echo Trevor's opinion in the sense that, you know, I felt working with my mentor was very good, but I don't think, to be honest, I felt that I was doing much with regard to the community. You know, this is very nice. It's good to speak to other people, kind of get a chance to interact with others through code. But certainly, I think for myself, that project was quite insular. It was me working with one other person, sort of writing these tickets and then throwing them out there, really.
Thank you. I will take note and hope to improve that in the future. All right. Do we have any other questions from the audience?
So if there are no questions from the audience, I actually have another one for David on his talk, actually, which is just
go ahead.
You showed us that when we have congruence 3 matrices, then we have a different our modular group base becomes 3, and we have this quotient structure. Is there a sort of generic structure theorem for if I take different congruent subgroups, and what does it look like? Okay.
No, we know that they are finitely generated, but we don't know exactly the structure. But well, I said no, but maybe I'm just not aware of this result. But I did some experimentation last summer. I did to find the relation between the generators. I did a script on SageMath. And I didn't find any patterns, but yeah, that's a good question. Yeah.
I also have a quick question for you. Sorry to interrupt. Okay, so I know lately a lot of effort is put into Sage to refactor code and to make the hierarchy and the theory stuff right. And I wonder, like for the modular form ring and Quasimodular forms, what is the main benefit of putting them into the right category instead of just the Sage object?
I think that it was basically to perform an operation between the elements, because before, when you created the ring of modular form, it was just it would return you the ring of modular form. And you could find some generator, but the generator return were just maybe modular forms. You couldn't even perform operation between them, or you could not. Basically that was. Or you could return some Q expansion, which were just power series in Q. So and now we can create the polynomial ring in. Over the modular form ring. So
before inviting you to the talk, I looked at your code. It was so neat, and I'm not very good at defining the Sage classes and components, so maybe I have question later. How can I reach out to you? Are you all active on Zulip?
Yeah.
Excellent.
Yes.
Excellent. Okay.
Just on
okay.
that, actually, sorry, just to interrupt again. Is that, I saw you use an is homogeneous method when you were talking about these elements. Is that generic for graded rings, or is that something you had to implement?
No, that I don't think it's generic for graded ring. I did implement it. I think it could be interesting to make it generic for a graded ring. Well, in fact, for graded ring, it's a little bit strange. There's no really generic method for accessing the homogeneous component or even yeah. So maybe that could be good to revisit this. I think there was a raised hand.
Hi, I have a question for you all. I'm new to the Sage 2. I'm the first year GSoC, and I want to know, like, kind of know the workflow. Like, do you design the code, like the structure first, and then going to implement, or how do you work with that? And after you design, do you push it to ticket and talk to your mentor, or how that works?
Well, first off, welcome. I'm glad that you're doing it this year. My workflow was I tried to write down all of the tests that I would want to do and do the examples by hand, because I think the testing, writing the code is much easier than the testing and then figuring out why your code's wrong. And so I think for me, like having a robust set of examples was like one of the first things I did. I think my mentor asked me to push track code every day. Initially, I was embarrassed to do that because it's like public, like now everyone in the world can see my bad code. But I think at the end of the day, it's maybe not necessarily every day, but every day or two. And then, you know, if you have problems on your own computer, or if your machine blows up, then it's everything you've done is backed up. So there's a good reason to do it. But I would be curious to hear from others what their workflow is like.
Yeah, me personally, it was similar. I would push to a ticket, even if what I did was not really perfect. My mentor would be there to check my work, and yeah, I think what advice I could give you is to not be afraid of making error. Your mentor will check it, and you will learn from your errors. And yeah, also my mentor asked me to review some ticket, also 1 ticket per week about. And yeah, so that reviewing ticket is useful too, because you actually have to go over someone else's work, and you learn about something new in SageMath and how to yeah. But,
Thank you.
I would say I probably had, that all sounds like good experience, probably not what I did. I think I pushed rarely and didn't review many tickets, so perhaps that's a bad thing. The one thing I would say, which I think worked quite well, is I was fortunate that there was sort of one main component of Sage that I was editing. So actually to speed up my editing, to make it better, I sort of, you know, took a copy of that one file, could make local changes to that, and just load that. So Riemann surfaces.py is basically where a load of the Riemann surface functionality is. So I had a copy of that, would just load that local version of my machine to sort of test and use it. And then, yeah, I think that saved me a lot of time in sort of recompiling and rebuilding. But I was quite fortunate that was only one file, so there was no sort of bigger architecture to work with.
Thank you very much for sharing. These are really good suggestions. So if we don't have any more questions, then we will conclude the session. Thank you again for the speakers for your contributions, and hope to see you in the community for a long time from now. Okay, we'll take a short pause.